so today we're going to go over your homework, and we're going to go over specifically the Atwood machines because I think those are the most difficult. So in a regular Atwood machine, which is just two masses attached by a string over a pulley, you have mass 1 and mass 2, and in this case, mass 1 is 50 kilograms and mass 2 is 100 kilograms. Mass 2 is bigger, so this thing's going to rotate with mass 2 going down. So any force going down is positive for mass 2. And for mass 1, since it's going up, any force going up is positive. So when you draw your diagram for mass 1, you want to show the tension going upward and its weight going downward. And when you write the net force equation, it's going to be tension minus its weight causes mass 1 to accelerate. For mass 2, it's moving downward, so it's going to be its weight minus its tension, because tension will be slowing it down, causes mass 2 to accelerate. And for the net force diagram, for the total mass system, just imagine that if you thought about these two masses as one big unit, mass 2 would be pulling it downward, but mass 1 would be slowing it. So the weights of them. So you only need to have mass 2's weight and mass 1's weight, Fg2 and Fg1. And it would just be Fg2 minus Fg1 causes the total mass, M1 plus M2, to accelerate. And that's the easiest equation always to use to find the acceleration. You always use the net or total mass system to find the acceleration because it doesn't have tension in it. It's just got one unknown. It should be 3.27 meters per second squared. And then you can plug it into either of the other two equations and you should get a tension of 505. The next Atwood machine, I think this is the most difficult one because I didn't do one just like it, but I did do, it still works the same way. You have mass 2, and it's going to be drug up the incline by mass 1 falling down. So mass 1 is the easiest one to do, right? Because it is exactly like, not mass 1, sorry. It is exactly like, mass 1, yes, I'm right. It is exactly like the hanging mass in the other one. Its weight is pulling it downward, and its tension is slowing it down. So its net force would be F2G minus tension causes M2 to accelerate. The most difficult part here is that this had friction in it. So obviously friction is between the box and the incline. If I'm telling you the coefficient of friction on the incline is point whatever, the friction is on the box on the incline, not on the box that's hanging. So just in general, you have, if you were to look at just the inclined plane, and we'll look at the one up here, you have F parallel causes it to go down the incline. You have F perpendicular, which is what the normal force is. That's really important for when you find friction. And then you have weight. But in our diagrams, it's rearranged a little bit, right? So there's a string tied to it. So there's tension pulling it up the incline. There's F parallel tending to make it slide down the incline. So it opposes tension. And there's FF too. And since the box is going up the incline, FF has to be opposing motion too. So most of you either had friction or you had F parallel, but you didn't have both. It's very important that if there's friction on an inclined plane in an Atwood machine, that you have both of them. Because in order for this to rotate, Fg2, the mass that's hanging, its weight has to overcome both of those forces in order to drag both of them, right? So the net force equation is F2G pulling down on both masses and FF and F parallel opposing it. So when you calculate those, you need to use the right formulas. Use the formula for F perpendicular to 5Fn. Then when you find friction, it's just mu times that. And use the formula for F parallel. And weight is always mg. So you're definitely going to have an inclined plane problem on your test, and you may have an Atwood with an inclined plane. So if FG2 is bigger than F parallel plus FF, then it will slide. So FG2 is 392, and when I calculated both of these, F parallel and FF, I've got a total of 126, so yes, it's going to slide. And if I wanted to find its acceleration, I would just say 392 minus 126 equals the total mass times the acceleration. For a box on a flat surface that has friction, you're going to have tension pulling it to the right. You're going to have friction pulling it to the left. You'll have a normal force that balances the weight. So you'll have to put all of those forces on that diagram. And it's important for you to do the normal force and the weight, because when you find friction, it's mu times the normal force. So in the inclined plane, the normal force was F perpendicular. It wasn't just mg, it was mg cosine theta. But for a flat surface, normal force is always weight. So when you find that friction, you're going to be using that normal force to find the weight. And then the mass that's hanging has the same diagram as usual, and the total mass, F2G, has to counteract FF. So this is going to rotate if F2G is bigger than FF on the table. And then you just subtract those two forces and set them equal to the total mass times acceleration to find the acceleration if you were asked that. All right, so that's basically what I wanted to go over, because I think it's really important for you to understand those Atwood machines, and I know they're difficult because it's two masses. For you to practice, let me just show you where you should practice. Actually, if you go back up to Module 4, there were two games up here that I think are really good. The balanced and unbalanced forces, because that kind of gets you thinking about when things are accelerating and relates the dot diagrams to it. But also the free body review game helps you think about different scenarios and what those particular forces would look like on those scenarios. And there's even a video that shows you how to play that game and what to look for. So I would really, this will help you, because obviously I'm not going to give you a bunch of open-ended problems to grade. I will have one pulley problem on there, and you'll have to draw a vector diagram, and it could be any one of those three types of pulleys, right? And it could have friction in it, or it could not have friction in it. It would be easier if it didn't have friction in it, wouldn't it? But this will help you, the worksheet will help you review those. But the free body review game will help you answer multiple choice questions where you're given a scenario and you have to pick what you think the best free body diagram is in multiple choice. So I would definitely review that. That's definitely a good